Alright, so you thought stars were big, but galaxies take it to the next level. Galaxies are a collection of sometimes upwards of billions and billions of stars, and they are extremely huge. Um, if you ever thought that traveling to other stars was unrealistic, um, even in the craziest sci-fi shows that we have, traveling into other galaxies is not really done. Star Trek, which is a vision of the future where we have warp drives and can travel extremely fast. Um, we've barely explored a quarter of our galaxy. They break it up into like four quadrants, and um, I forget. I think we're in the alpha quadrant in that universe, in that fictional universe. But long story short, galaxies are huge. This is a beautiful picture of the Sombrero Galaxy, which you can see almost edge on. It definitely looks like a spiral galaxy, and very bright in the center, a lot of stars there, and a lot of dust and gas in the disk blocking light from stars behind it. We actually see this in our own Milky Way, and we're right inside. So back in the day, a guy named Edwin Hubble decided to spend much of his life photographing and categorizing all the galaxies he saw, and he made four main categories: spirals, barred spirals, ellipticals, and irregulars. If you look on here, you got the ellipticals over here, E for elliptical, S for spiral, SB for barred spiral, and IRR for irregular. And this is kind of the bridge between the spirals and the ellipticals, this one here. So let's go into more detail about those. Spiral galaxies. Here's a lot of nice examples of spiral galaxies. They contain a flattened disk in which spiral arms are formed. And in all these, you can see spiral arms. Some are more obvious than others. This one looks like an arm here, maybe an arm here. Yeah, this arm going out here. This might be the continuation of this arm. A little easier to see arms in this one. That looks like we got an arm here. Might extend out to here. Here we got an arm. Maybe an arm here. So beautiful arm structure. And we denote these galaxies by the letter S. And they're also subclassified as either A, B, or C, or according to the size of the bulge and the tightness of the spiral. This is an example of an SA galaxy. Here's an SB galaxy. And you can see down here the letter. And here's an SC type of galaxy down here. SA has the largest bulge, and SC has the smallest bulge. Most spirals are not seen face on, but rather tilted or on edge. There's a lot more angles, examples of angles between 0 and 90 than there are just 90 or just 0. So you're more likely to see it somewhat tilted. And a major characteristic of spirals is their abundance of gas and hot newborn stars in the disk. Lots of star formation happening. These are very active star creating galaxies. Then we get the barred spiral galaxies, and very similar to regular spirals, but they have this little extra sort of bar shape. Bar, bar, bar in the nucleus, in the center of the galaxy. So they differ from spirals due to the bar of matter passing through the bulge. We denote them by SB, and then there's SBA, SBB, and SBC, the same as with spirals. And you can see the examples of each here, A, B, and C. Most astronomers, though, don't actually differentiate between barred spirals and regular spirals. They just call them spirals. And actually, it's thought that our galaxy is a barred spiral based on how the center of the galaxy looks from our point of view. So we're guessing it's either an SBB or an SBC. And then you get the ellipticals. These galaxies have no spiral arms and appear actually to not have a galactic disk either. They're not really flat. They're more like egg-shaped. They're denoted by the letter E for elliptical, and we divide them into 8 categories, E0 to E7. where E0 is the most circular and E7 is the most elongated. We have three examples here. Here's an E2, almost circular, not quite. It looks like a little longer along this axis. Here's an E3, kind of egg-shaped, and E5 is really straight out, like elongated. And these galaxies tend to be much larger than regular spirals, with little cool gas. So that seems to be evidence that these are old galaxies. And large, probably because of a merger of multiple galaxies into one big galaxy. And then we got sort of the middle ground, SBO galaxies. They're between spirals and ellipticals. They do contain a disk and a bulge, but seem to have no spiral arms or gas and star formation in these absent arms. So kind of the bridge between the two. This is an SO, and this is an SBO because it looks like there's a bar going across there. Then we get the irregulars. These are the galaxies that don't fit in with the others because they just have an irregular shape. They definitely are big collections of stars, so they're not pure nebula like gas clouds and dust clouds. So they're still considered galaxies, but they don't have a nice regular shape. These tend to be rich in interstellar matter and young stars, and also tend to be small. We call them sometimes dwarf galaxies. Um, these make up the majority of galaxies along with ellipticals. Spirals are not in the majority. Yeah, we tend to either denote them as irregular 1 or irregular 2. Here's some examples of some irregulars. Alright, so back to this picture, the Hubble sequence it's called. This is often called Hubble's tuning fork because it looks like a tuning fork. We got one bar and then we split up into two branches here. And Hubble actually believed this to be an evolutionary track starting from the left and going to the right, starting off nice circular ellipticals and then spreading out and eventually becoming spiral, the arms starting to form, and then maybe sort of dying as irregular galaxies. But we actually find no evidence of this, even though we still use this as a classification system. If anything, it probably goes backwards this way. The Hubble Deep Field. So we got this crazy telescope out there, which soon won't be the craziest. Can't wait for the next telescope to go up. It's awesome. The Webb telescope. But the Hubble is freaking amazing. This is a picture of deep, deep, deep space, really far away. Basically, all you see here are galaxies. You see one, maybe two, three, four, five, six, maybe six stars. You probably can find more if you look closely. These are stars in our galaxy, because obviously if you're looking out in deep space, you got to look through some stars. Here's another one. But by far, mostly what you see here are galaxies. In fact, looks like a big cluster of galaxies here that are actually gravitationally lensing. In the last video, we talked about Einstein's theory of special relativity and how matter warps space and time, and even light is bent. Well, here's an example of light being bent. So this is light most likely coming from behind this big cluster of galaxies, and it's being bent around and lensed around. And we could create computer simulations to extrapolate these back based on the mass distribution here and maybe get a clearer picture of what this stuff might look like behind. Kind of cool. It's like a telescope in a telescope. The Hubble telescope is able to see this far, and then these galaxies magnify what's behind it again. Cool. Here's a picture of our Milky Way. This is the galaxy we live in, and of course here is the center of our galaxy. We're out in the outskirts in one of the arms looking in towards the center, and then this right here, this sort of bar shape is why we think we might be in a barred spiral. So, typical spiral galactic structure. Well, we believe our galaxy is a spiral, so we can take a look at our galaxy first. Our solar system lies in the galactic disk, so we got spirals tend to be flat, so they have a disk, and this is the galactic disk, this like long flat region. And our solar system is thought to be out in the outskirts, kind of not quite near the edge, but pretty far out, away from the galactic center. And the disk is only about 300 parsecs thick, which is still a crazy huge distance. But relative to the width of the relative to the width of the galaxy, it's basically nothing. It's almost like the rings of Saturn. They're pretty wide, but they're very, very thin. They seem paper thin in comparison, even though um, even though when you actually go into the rings, they're sort of thick. And the disk is thought to be about 30,000 parsecs in width. Um, I don't think I've talked about a parsec before. Parsec is another distance used. It deals with parallax. You can look it up if you're interested. If I remember right, I think a parsec is about 3-ish light years. I'm going to pause and Google it real quick. Yeah, about 3.25 light years per parsec. So it's on par with a light year, but slightly bigger. It's kind of like, not quite like a mile versus a kilometer, but sort of same idea. So anyway, 30,000 parsecs is about almost 100,000 light years. Woo. So in our own galaxy, if we look at one edge of it, of course we can't see across as you saw in the earlier picture because all this stuff is blocking our view. But if we could, it would take light 100,000 years to make it here. It's pretty big. Wow. Our position in the Milky Way does not allow us to study the overall structure, as I mentioned, because, again, all this stuff in between us blocks the farthest parts. A good analogy for this is if you're in a forest. If you're flown over a forest in a plane, you can see basically what the forest looks like. You can see how big it is. You probably see the edges of the forest, unless it's super huge. You can tell if there's like holes in the forest, like where trees are cut down or something, or if there's a river in the forest. But if you're in the forest, then you can only see maybe a few 100 feet in either direction, and you have no idea what the rest of the forest looks like. There's actually a cool scene in The Hobbit, both in the book and the movie, where they're in Mirkwood and they're just like, I hate this forest. It's so dark and scary. Where are we? And so they have Bilbo climb up to the top of the trees, and he thinks he can see maybe actually he doesn't really think he can see the edge. It looks like it just goes off forever. Cool scene. I always loved that scene as a kid when I read the book. And continuing on with the structure, in the middle of Spiral Galaxy, we got a galactic bulge, which you can see here. It bulges out up above and below the disk. In our galaxy, we're about 8,000 parsecs, 8 kiloparsecs from the bulge. And this is a region of the galaxy, like I said, that goes up and down below the disk and above the disk. And it's thought that a supermassive black hole is in here near the center of the bulge, which is the center of our galaxy, and that it gravitationally controls our galaxy. Everything sort of orbits around that. Pretty crazy. Size and shape of our galaxy. So continuing on with that, so here's the bulge, here's the disk. We also got what we call the galactic halo, which is almost a spherical, just really big sort of cap or cover, or I don't know, just surrounding our entire galaxy, and made up of a lot of globular clusters, which are clusters of old stars. And what's cool about that is they orbit kind of randomly, like, and I'll talk about that in a later slide. The stars in the disk, they orbit around just like planets orbit around the sun. It's very regular. But these guys, this guy might go like whoa that way. This guy might go whoa that way. So they don't really orbit very regularly. So that's a clue that these clusters probably resisted the initial formation of our spiral arms. And there's little or to no new stars forming in the halo and in these clusters. These are all pretty much old stars, dying stars, or on their way to dying. So how do we know what's going on rotationally in our galaxy? Well, we can use the Doppler shift, redshift and blue shift of light. So here's our sun. This is towards the galactic center. If you look at stars over here, they're blue shifting, meaning they're coming towards us, so they're moving faster, catching up to us. In general, coming towards us. Of course, if they're moving faster here, they're moving faster here, but they're going away from us, so they're going to be redshifted. Stars out here, though, are moving slower, so we're actually catching up to them. And so stars over here, we're catching up to them, so blue shifted. And here, we're moving away from them, so red shifted. Nice little sort of puzzle to describe our motion in our galaxy. And it's thought that based on where we are, it would take about 225 million years for the galaxy to rotate, which is quite a long time, but definitely not as long as the Earth's been around. And so we've probably gone around the galaxy quite a few times in the Earth's lifetime. And there is differential rotation. The closer you are, the faster it rotates, and the farther you are, the slower it rotates. And that's why you can see these red shifting and blue shifting patterns. Orbital motion. Oh yeah, this is what I was saying about the random motions of the globular clusters in the galactic halo. So you get the spiral disk pattern that moves in a nice orbital, periodic orbital pattern, and the clusters just go around wherever they want. It's thought that the Milky Way formed from kind of like stars in a sense, from younger star clusters, gas and dust, and of course they're not going to directly collide into each other. They're going to probably like move near each other and then spin around each other and then combine, and that's going to cause a rotation. And then you basically get a flattening out like the planets in our solar system did, and then you get this nice spiral shape. So many of the stars, these old stars, are now thought to be in the halo. And then eventually you get this spiral pattern, and it's thought that if this is kind of what our galaxy looks like, the Milky Way, we're probably out here somewhere at the edge of one of the arms. So if these spirals come because the galaxy is rotating and winding up, how come it doesn't just keep winding up and just create like crazy numbers of spirals? We don't really see this when we look at other galaxies, so there must be some other thing going on. What might that be? Well, it's thought that instead of the arms actually moving around, what's moving around is a wave, a density wave, kind of like how sound moves through air, but the air doesn't move. When you talk to someone, you're not pushing air from your mouth to their ear. The air near you stays near you, but the energy wave from your vocal cords passes through the air. Same idea here. You got a density wave of some sort passing through the gas and dust and stars. And a good analogy of that is like a traffic accident. Some disturbance is causing more density to be here, and so this is kind of like a density wave. And if this truck were to be moving slowly down the road, and the workers are moving the cones, that density wave would move down the road as well. What might have caused the initial density wave? Don't really know at this point. And here's another cool thought about star formation in the arms. Kind of the cycle of life where stars die off and give birth to new stars. So here you got, just kind of ignore the sides for now. Here you have some stars that have been in the main sequence, and they are reaching the end of their life cycle. They all would have formed roughly the same time. So when they die, they start blowing up, supernovaing. And when they do, they make shock waves that go out, 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 out. And those shock waves push together, like exert pressure on nearby nebulas and gas and dust, causing them to collapse and form new stars. And so it's thought that this is how star formation works in the spiral arms, and that this might be sort of like linked to the density wave traveling through. Alright, now the last main topic are the other 25% of the galaxies besides the spirals, ellipticals, and irregulars. These are active galaxies, and They're called active because they're extremely bright, not necessarily in the visible, but in basically all other wavelengths. So here's a normal galaxy, and you can see most of the light is from stars in the visible part. And an active galaxy is much brighter in all wavelengths, not necessarily just the visible. And there's three main types: Seyfert, radio, and galaxies, and quasars, although it's thought that they might be kind of one and the same, which I'll talk about in a sec. So the Seyfert galaxies, these resemble normal spirals. In fact, if you didn't look at them in the infrared, you wouldn't even really know that they're not the same as typical spirals. But if you look at them in the infrared, you find that about 75% of the light coming from them is in the infrared. So they don't look bright to the human eye, but they're really bright in the infrared, so something's causing that. Then you got radio galaxies. These emit large amounts of energy in the radio part of the spectrum as lobes, kind of like jets going out. So here's a radio galaxy in the visible, and it doesn't look all that different. It looks like you're viewing it edge on. But then if you look at the radio, you see whoosh, lobes of radio stuff being emitted. And if you superimpose these two, then here's the visible part, and then here's the jets coming out. These galaxies can emit 10 times more energy than our galaxy at all wavelengths. And that's what you're seeing in this picture here, at all wavelengths, not just visible. And although they're easy to see in radio, they actually emit light in all wavelengths. And if these lobes are pointing towards us, kind of like the pulsars, they're kind of like lighthouse beacons. If these lobes are pointed towards us, we call them blazars. So that's kind of like from this direction. If you look at if you're able to see these lobes from the side, kind of like this, then they're just radio lobes. And then we got quasars. So when astronomers first pinpointed one of these objects, it appeared to be redshifting about 16%, which is a lot. That basically means that they're really far away. So when we talked about the Hubble constant in an earlier video, that's kind of what I was talking about. The farther away something gets from us, the faster it moves away from us, and the more it redshifts. So 16% is a huge redshift. That means they're moving away from us at about 48,000 kilometers per second, and that really far away. Maybe on the order of 1,000 megaparsecs, mega meaning a million, very far away. These are thought to be the brightest objects in the universe, and that they're an early step in galactic evolution. So what is the engine of an active galaxy, sometimes called active galactic nuclei? Some theories suggest that all active galaxies are the same thing, because they share the following properties. They're very bright, high luminosity. Most of their energy is from non-stellar objects, at the core, or at the nucleus of the galaxy, not at the stars orbiting. The energy output can be variable, which we'll see why in a second, and then they often exhibit jets, like radio lobes. So it's believed that the extreme brightness is driven by supermassive black holes, millions, if not billions of times as massive as our sun. And if you remember when we talked about binary companions and a white dwarf stealing stealing mass from their companion, and how when it did that, it became very bright and was called a nova. And if it stole enough mass, it actually would explode in a supernova. It's thought that a similar thing would be happening, except instead of stealing mass from one binary companion, the supermassive black holes would be stealing entire stars, consuming entire stars. Of course, the reaction from that is extremely violent, giving off huge amounts of energy, and the variable output could be from different stars being consumed at different times. So one star consumed, bam, crazy jets of energy. Another star, bam, later on. So kind of cool. All right, that's it for galaxies, and I'll see you next time.